Greetings everyone, this is Mr. Mull, and in this video we're going to be getting an introduction into work and energy, and by the end of the video you're going to be able to define work and be able to use the equations for work to perform calculations. You're going to understand what the different signs mean for work, and you're going to be able to analyze a force versus distance graph to find the work done. Let's go ahead and get started with some definitions. Feel free to pause the video at any time in order to write anything down that you think is important. So let's start with the definition of energy. Energy is a substance-like quantity with the capability to produce change in physical systems. I say that energy is like money in the fact that we can gain money, we can lose money, we can have no money. Energy is kind of like the currency of physics. It enables us to produce changes in physical systems. Work is closely related to energy, and work is the amount of energy transferred into or out of an object or system by mechanical means, and by that I mean with forces. So we're pushing or pulling objects, and we're putting energy into a system or taking energy out of it. So this is an equation from your equation sheet that I broke down for you. Delta E is the change in energy of a system. It can be positive or negative, and the change in energy of a system is also known as work. And the two forms of the equation that you'll find on your sheet are F parallel D and then FD cosine theta. And so looking at this here, F parallel is just the force or component of force that's acting parallel or in the direction of the displacement. F is the force acting, D is the displacement through which that force acts, and then cosine of theta. Theta has a very special meaning. It's actually the angle between the direction of the force and the direction of the displacement. The unit of energy is the joule, and a joule is defined as the amount of energy needed to apply the amount of energy transferred into an object when it's moved 1 meter by 1 Newton of force. And then when I break down what a Newton is, you also get this other unit for work, energy. Okay, so we're going to talk a little bit about the different signs of work. Work and energy are scalar measurements. They're not vectors. But the positive, negative, or zero values of work still have meaning. So positive work, think of it like you're getting money in your bank account. I put it in green here so you can see that energy transferred into an object. So when I have energy transferred into an object, when I'm applying that force, it's always going to be in the direction of the displacement, or there's going to be some of that force that's going to be applied in the direction of the displacement. So you look at my little force 1 and force 2, both those forces are applied in the direction that the object is moving or has displacement, so we're actually adding energy into the system. Negative work is when we have energy transferred out of an object. Think of this as being you're losing money out of your bank account, you're getting a withdrawal. So we're losing energy. So if I have this object moving to the right and I'm applying a force number 3, then this is going to actually take energy out of my object. It's probably going to be slowing down or something like that. And then we have zero work is if there's a force applied and there's no energy transferred via that force, then we have zero work done by that force. So force number 4 is moving to the right, and so that force is actually applied in a completely different direction. It is not going to be adding or removing any energy to my system, so there's zero work done. So let's try a couple example problems. So we're going to start with the first work energy example. It says a 3 kilogram block is sliding across a frictionless surface. So I'm going to be assuming that it's sliding, it doesn't say this, but to the right. And, oh, there we go. If the force acts as the block moves 3 meters to the right, calculate the work done by the applied force during the slide. Okay, so we want to find work. They give us a distance moved, and we have this applied force here. So I know that the displacement was to the right, and that was equal to 3 meters. So I'm going to go ahead and draw my little, here, I'll put that there. draw my little displacement there, and that little displacement was equal to 3 meters. And so what I can do now is I can look at my equation for work done, and the work done by this applied force is equal to that applied force times the distance over which it acts times cosine of theta, which is going to get us just the parallel component of that force. So I can go ahead and look at my applied force. It was 20 newtons. And then the distance through which that force acts was 3 meters. And then cosine of theta, I need to look at the angle between the displacement and the force. So the force was applied back here, and then the displacement was over there. So we're looking at this angle here, and we have 90 degrees plus this little 35. We're looking at 125 degrees difference between those two vectors. And so we're going to go ahead and put cosine at 125 degrees. And then we're going to get that we'll make sure our calculator's in degree mode. We're going to get negative 34.4 joules. And the fact that this is negative is totally fine. It doesn't mean anything about direction, but what it does mean is that my object has actually lost energy that it had by this force being applied in the direction opposite that it was going. Alright, let's try another example, a little bit more complicated with something done on an angle. So this is our next worked example, and we have a 20 kilogram block sliding down a 30-degree incline at a constant velocity. So I'm going to start by drawing a little picture here. So we've got a 30-degree angle, and we have a block, and it's sliding down this incline. So that means that I'm going to go ahead and draw my little, so my displacement here, it says calculate the following as the block slides through a distance of 2.1 meters down the incline. Okay, so we've got a distance that was traveled. Let's draw some forces on here. So there's obviously a lot of forces on here, and I actually want to find the work done by each force separately. So I'm going to go ahead and draw my forces here. We have our normal force acting perpendicular to the surface. We have our force of friction, kinetic friction, of course. It's definitely sliding. We have our force of gravity, vertically downward. And that's going to be our diagram. Now, one thing I really want to, now it says we're moving at a constant speed. So I noticed that in my new coordinate system, I'm going to go ahead and break my force of gravity, and we're going to make down the ramp be our positive x direction. Just want to break this into little components here, like we usually do. So there's our little FGX, and there's our little FGY. Okay, so here's our picture. So we want to find the work done by gravity. I'm going to actually show you two different ways you can do this. So if I want to find the work done by the force of gravity, I can use the equation we just looked at, and that would be that applied force times the distance through which it acts, and then cosine theta is going to be that angle between the direction of the force and the direction of that distance. So I remember that Fg is just m times g. And so I can actually look at the direction that force is acting. So the displacement is down the ramp, and then the force of gravity is going to be this distance away from the displacement. So I've got to figure out what that force is using what I know about this, this little triangle. This is actually 30 degrees. So that means that down this ramp here, that this is going to be 60 degrees between Fg and the displacement. So I can go ahead and put my force of gravity was m times g. We've got a 20 kilogram block times 9.8, and then the distance through which that force acted was 2.1 meters, and then we're going to use cosine of 60 degrees, which was the angle between the displacement and the force of gravity. And when we do this, we're going to get a positive value. Gravity was adding energy to this block of 205.8 joules. Okay, totally works well. Now the other way that we can do this is I can look at that second equation, and that second equation said if I wanted to find the work done by gravity, I can take the force that was acting parallel times the distance through which it acted. So when I look at my little diagram here, that parallel force that was parallel with the displacement was actually this little FGX here, which is just mg sine of 30 degrees. So what I can do then is I can rewrite this, that the work done by gravity is equal to, okay, I'm just going to erase this little g here, okay, F parallel d. So FGX was the parallel, the force acting in the same direction as the displacement, times d, and then FGX was just mg sine 30. So we have 20 times 9.8 times sine of 30 degrees over that 2.1 meters. And what we're going to find is that it's going to be the exact same value. Either way we look at it. Whether we look at that whole 60 degrees for the entire force of gravity, or we just look at the force or component that was actually acting in the direction of the displacement. And either one of those are going to be okay to use. Okay, I'm going to do part B, what is the work done by the normal force? And when I look at the normal force and the direction of the displacement, we're going to notice that the angle is 90 degrees. So that means the work done by that little normal force is actually going to be 0 because it is 90 degrees. Cosine of 90 degrees, when I'm looking at that first equation, is going to make it go to 0. So normal force didn't actually do any work here. All right, the next question says, what is the work done by friction? So taking a look back at that diagram, you'll notice that because we're moving at a constant velocity and the acceleration is 0, then we know that that force of friction is going to have to be balanced with that little FGX that we looked at. But the force of friction is acting 180 degrees away from the displacement. So let's take a look at the work done by friction. So we have the work done by that force of friction is equal to the force of friction d cosine theta. And remember a second ago I showed that diagram. That force of kinetic friction is equal to FGX for this problem because we are moving at a constant velocity and the acceleration is 0. So what this means is I can plug in mg sine 30 again. 20 times sine of 30 degrees times that distance times cosine of theta. And cosine of theta, friction was acting 180 degrees. Now what that cosine of 180 is actually -1. So what's going to happen is it's going to invert the sign, and we're going to get negative 205.8 joules of work being done by friction. Okay, the book, when it talks about work done by friction, will call this thermal energy, or delta ETH. Okay, the idea is the exact same thing. The work done by friction to heat up the block and the surroundings would be negative 205.8 joules. The last part of this question says, what is the net work done on the block? And net work is kind of like net force. All we have to do is add up each individual works done by different forces. So we had 3 forces acting: the normal force, the friction force. So if I add up all the work done by each one of those, including the sign that came with them, I'm going to get the net work. So gravity was adding energy to the block. The normal force was not doing any, was not adding or removing any energy, and the force of friction was actually all the energy that gravity was giving it. It was removing it and turning it into heat as it was going down the ramp. So what we have is that the net work done by the block was actually 0 joules. And the other way we can think about this is that the net work is just equal to the net force times d cosine theta. And because the net force in that was 0, because it was not accelerating, there was no net force, then we know that the work would also be 0. All right, one last little thing. We have a little wrap up. Oh, nope, we got to do force versus time graphs. Okay, so we know that the force times the distance is essentially the work done. And so this is a graph showing a force versus distance compressed for a pillow that's exerting a force on an egg as it brings it to a stop. Use the graph to calculate the work done on the pillow during the entire 15 centimeter stopping distance. Okay, so in this problem, we're exerting a force on an egg, and when I'm looking at this graph, I'm noticing that the force is changing. So I can't just multiply a force times a distance because the force is actually changing here. So what I'm going to have to do is, looking at this graph, I notice that I have force on the y and distance on the x. So if I were to take the area of this graph, okay, length times width of these shapes, the area underneath them, we're going to get that area is going to be a force times a distance. And so because of this, the work is going to be equal to that area under the curve for this type of graph, which is a force versus distance graph. So what I can do is I can break this into 3 little shapes. We've got a little triangle, 2 triangles, and a square. So if I take these 3 shapes, I'm going to go ahead and add that area is going to be a triangle plus the triangle plus the rectangle. And when I do that, I'm going to take the area of the first triangle, was 1/2 the base times the height. The height was, looks like they gave it to me in centimeters. I'm going to convert that to meters, 0.03 meters, times the force applied during that, or the height of that little area, which was 30 newtons, plus, I'm going to add that other little triangle, 1/2. The base would be 0.12 meters times the length, or excuse me, that little triangle was 10 newtons tall. And then we have that big old rectangle is 0.12 meters was the distance, and then 30 newtons was the height. So when I add all those together, we're going to get 4.65 joules. And that's going to be the force for a pillow exerting a force on an egg, bringing it to a stop. And this is actually positive for the pillow because the pillow was getting the energy that the egg had. All right, let's see how you guys did with these ideas. Wrap-up question. An object is tied to a string and lowered from a height at an increasing speed. What is the sign, positive, negative, or 0, of the work done on the object by each force acting during its descent? Why don't you go ahead and pause this video and try to answer these questions, and then come back in a second. All right, the first thing I want to do is analyze what's going on. So if I have something tied to a string, but it's increasing its speed, and it's on our planet, then we know that the force of gravity and the force of tension are acting, but if it's increasing speed, then it's accelerating downward. So when I'm looking at these values, I'm thinking a couple of different things. I can look at, is this force adding or removing energy, or we can actually look at the angles involved. So the work done by gravity, it's accelerating downward. This actually was going to be positive work. Energy was going into the system by gravity, so this was positive energy. The other way we can think about it is that that force is acting 100 and cosine, it's acting 0 degrees. So it's acting in the direction cosine of 0 is going to be positive and that force is going to be a positive value as it travels some distance. The work due by tension, tension is resisting this acceleration. It's going to be removing energy from the system. The other way we can think about it is the cosine of that angle is 180 degrees in relation to that the displacement that object is moving. So the work done by tension is actually going to be negative. And then the net work done on the object is going to be the work done by the net force. Because it's accelerating downward, the net force is going to have to be down. I know that the force of gravity is going to have to be greater than the force of tension. And because it's speeding up, we're going to have to have some energy being added into the system. So that's going to be positive. All right, this has been a wrap-up discussion on work and energy, and I hope that this has been helpful.